Hello, mathematicians! Today is our final lecture right before the review lecture, which I'm posting tomorrow. So we are going to cover section 6.2, volumes by cylindrical shells. So last section, 6.1, we discussed slicing, washer, and discs. And now we're going to do it by cylindrical shells. And so it's a little bit different. So kind of going to start off with an example like last time. So say we have this curve, y equal to 3x minus x squared, this guy right here. And I want to rotate it around x minus 1. We talked a little bit last time about rotating around another line. But in this case, you see that I have one curve, but I kind of have an outer radius. An inner radius and an outer radius. So that kind of causes some problems. So, what we're going to do, so I drew this picture down here, and the pink shaded is the parabola rotated around x equals 1. And then this yellow right here, this is the cylindrical shell that we're going to base our integral off of. So if I kind of take, like, if you think about like those donut cookie cutters, or just a cookie cutter in general, and kind of like squish it through the solid, I'm going to have this little cylinder that I can pull out to estimate the volume. And kind of that's what we're going to create out of this curve, all right? So we can also think about cylindrical shells like tree rings. So if I like take a tree log, and I can like make it almost into any shape by like, I can like grind it down and make a bowl and stuff like that. So that's kind of what we're doing. And those tree rings are gonna act like our little shells. And just like we had our rectangles when we were just trying to find the area under the curve, the thickness of the cylindrical shell is going to approach 0. So we're going to base our integral off of the fact that I can take a cylinder. So if this is one of my cylindrical shells, kind of looks like a roll of toilet paper, I can unroll it and I just get a rectangle back out. Its thickness is going to be delta x, just like we talked about. So the difference between the inside and the outside is going to be delta x, and you can see that right down here. And then its height is still going to be that y value. So if we could see whatever y was right here. Oh, we can't really see that in the pink. There we go, y. And I had a radius when I had a cylinder, but now I'm going to have a length. So my radius here, if we're looking back to from here, x equals -1 to whatever this point was, that distance from x equals -1 to whatever value I'm going towards, well, these are x values. So that's going to depend on x. So we can just call that radius 1 plus x. Similar to x minus the line that we are turning around. Since it's -1, it becomes a positive 1. So this length of the rectangle is now going to be the circumference of this shell. I know what you're saying, oh, there's 2, which one do I know to take the derivative of? Remember, the distance between those is delta x, and that's approaching 0. So if we just take the outer one, they're going to be technically exactly the same. Think of like putting like a little piece of paper down. Like it technically has a thickness, but like think of it as like 0 thickness. So our length is going to be their circumference, which is 2 pi times the radius, in this case 1 plus x. All right. And our height, we said was y, but we're given what y equals. It's 3x minus x squared. So we can continue on and I want to make sure I get this right. We get volume is going to look something kind of like length times width times height. So our length is 2 pi 1 plus x. Let's write it out. Length times, whoa, what the heck is that? Length times width times height, which in this case is 2 pi 1 plus x. Our height is y, which is 3x minus x squared. And our height, oh wait, that was width. Width is supposed to be delta x, but this goes towards 0, right? We would like add each one of these. We can call this like a v of k. So this is like x of k, and this is delta x. So if I add all of these up together like I would a Riemann sum, I get the volume is going to equal this integral from, I'm going from 0 to 3. Of 2 pi 1 plus x 3x minus x squared we don't have delta x, we have dx, all right? And then we can multiply this out and integrate just like I would with any other integral. And we will get 45 pi over 2. So that's kind of like a very generic background of how to get a formula for cylindrical shells. So we can generalize it and we'll get the shell formula for revolution about the vertical line, a vertical line. We talked about a horizontal line last time with the washer method versus if I had two curves in the disk method, if I just kind of moved over a little bit, right? So the volume of a solid generated by revolving the region between the x-axis and the graph of a continuous function, let's call it y equals f of x, and that's greater than 0. If L is some number that's below the range, so we had like -1, even though A was 0 and B was 3. So it can't really be in my limits of integration. I can't spin it around, that would be weird. So about the vertical line, x equals L. So that's gonna be, oops, I'm still in orange. Integral from A to B, 2 pi times the shell radius times the shell height. Dx. All right. So this is, it's going to be a little confusing at first, but practice makes perfect for these. All right. So we're going to do a few examples. The region bounded by the curve y equals square root of x, the x-axis, and the line x equals 4 is revolved around the y-axis to generate a solid. So, I don't want to use red actually. We'll make it another black line because it's a curve. So x equals 4 is right here. So I'm going to revolve. I'm going to take this area and revolve it around the y-axis. So I know how to revolve it around the x-axis, we did that last time, but now I'm revolving it around the y-axis, and it's not the area between the curve, whoopsies, and the y-axis, it's the area between the curve and the x-axis. So that's kind of where the difference is coming from. If you try to go from the y-axis, kind of using methods that we did last time, it's going to get too messy. All right, so I also drew this picture. I know I'm a really great artist, of kind of what a cylindrical shell would look like if when we rotated this around. All right, so this red line represents the shell height, which you can see in the right picture. So and we can think about that shell height as I'm going over the curve each time. It's going to be y equal to the square root of x. And then r right here is my radius. It's the distance from where I'm rotating around to the curve. Well, I'm going to start at 0 and I'm going to go until whatever x value I hit. So that's just going to be x. So we'll say that okay. The best way to do these is to draw a picture to the best of your ability. So let's plug and chug into my equation. I know what my limits of integration are, a and b, just by looking at this. I know I'm going to start at 0 and I'm going to go to x equals 4. I'm also told I'm bounded by it as well right here. So that means that volume is going to equal from 0 to 4, 2 pi. What is my shell radius? It is x. And my shell height is the square root of x dx. So even though I'm rotating around the y-axis, I am still keeping my terms. I'm still doing in terms of x, because the area of this curve that I've drawn in pink is found by the curve and the x-axis. Remember last section when we were doing rotating around the y-axis, I was finding it between the curve and y-axis. So that's the difference. All right, so then we can, let's pull out that 2 pi. Just a coefficient. So I'll get x to the 3/2 dx, which equals 2 pi x to the 5/2 times 2/5 from 0 to 4. And that's going to give me 128 pi over 5. All right. So not too much work in terms of integration other than like calculating this number. But it was difficult to see the height and the radius. After we do some examples, we'll write a, oh wait, that was not right. Was it right? Okay, yeah, it was right. We'll do kind of like a summary of what to do. So that was rotated around the y-axis. Let's do one that we actually already know. So it's, again, the region bounded by the curve y equals the square root of x, the axis, and the line x equals 4. And now we're revolving it around the x-axis. So we actually already did this one, and we're finding its volume by using the shell method. So we did this in 6.1 and we got 8 pi out. So this is kind of to show you that if you're like, shoot, how do I know if I should use disc, washer, or shell? As long as you choose the right components of each. Okay, washer is a little different. Maybe. If you choose the components correctly, you can almost use them interchangeably. Sometimes you saw up here how I can't use the disk method with this example because the area here is different than if I chose the area other way, right? So, okay, to find the volume of the solid by shell method. So I drew my picture, and now I'm going to find, we're gonna make R the radius of our cylinder. So if I have a cylinder, this way it was kind of like a cheese wheel. This cylinder is now going to have a radius this way. Which is this. So it was shell height up here, and okay, let's do this in the right color so it makes sense. So my radius is an orange. So now my radius is this way because I'm revolving around here. And my height is in red, and that's going to be the distance from the curve to x equals 4, because we are also bounded by that line, which I kind of forgot to draw. Shoop. Okie dokie. So red is our height, so that means that shell height is going to start at the curve and end at x equals 4. So to find that length, I do end minus beginning. So I'm going to do 4 minus y. So this is the tricky part about shell. It kind of switches your thinking. So remember, I kept everything in x's because even though I was revolving around the y-axis, now I'm revolving around the x-axis. So now I need to change things to be in y. I know, weird. So that's my shell height, and my shell radius is going to be the distance from 0 up to this curve, which is also just y. So our shell radius. So the shell radius is going to start down here, it's going to go up here, and so on. So it's going to be y. So we're going to put it together, and we get that it's 2 pi from, our things of integration. So we went from 0 to 4 in the x's, so that means we're going to go from 0 to, I have a little picture now, 2. And we can solve that by seeing where x equals 4 and the square root of x intersect, and that's at the point 4, 2. So we're using the y value. So we're going from 0 to 2. What is my shell radius? It is y times 4 minus y is my height, dy. So I get 2 pi 0 to 2 of 4y minus y squared dy, which is equal to 2 pi 2y squared minus y to the third, 0 to 2, which is going to equal 2 pi 2 times 4 minus 8 over 3. Ooh, wait, I missed something. Oopsies. There it is. This is not supposed to be y. This is supposed to be y squared. because if you think about it in terms of x values, this is x, so then y would be because we have y equals, oh my goodness, a little line. Ta-da! Okay, so that's why that's y squared. That changes these. So this is y to the 4th over 4 now. There we go, that makes everything a lot better. Two to the 4th divided by 4. It sounds like 4 to me. So 8 minus 4 is 4 times 2 pi, and we get 8 pi. Perfect, exactly the way we wanted before. I wasn't getting 8 pi, that's why I knew it was wrong. In my preference, I would rather use the disk method for this one, but this is just a showing away. If you're like, I kind of like cylindrical shells, go for it, totally fine. This is just another way to do it. And it's kind of, this example is to show that you can interchange the methods sometimes, but the integrals will look different. Okay, so let's do a little summary and then we're gonna be done. And then you have extra homework to do, if you so please. So, summary of the shell method. So this is regardless of the position of the axis, so horizontal versus vertical, right? Because it might not just be the axis you're revolving around. The steps are kind of still going to be the same. So we're first going to draw the region and sketch a line segment across it. So I'm going to draw the region, which the region kind of would be like this 2D, not the 3D one. And I'm going to sketch a segment across it. And it's going to be parallel to the axis of revolution. This helped me a lot when I was learning this, is to draw these pictures and to know, okay, cool, draw that line parallel to the axis. Then we're going to label that segment. So either it's height or length. So here it was my length. Here it was my height. And I'm realizing these are I'm just gonna move them down. So I'm gonna label its height or length, depending on height, if it's parallel to the y-axis, and length if it's parallel to the x-axis. And I'm gonna call that shell height. And the distance from the axis where we're revolving, so axis of revolution, and we're going to call that our shell radius. Right, this is honestly the most important step to me. So up here, I was revolving around the x-axis, so I drew my line parallel to the x-axis. I didn't mean to erase this. Bloop, doop, 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 doop. And then, so that in red was my shell height. I went to my curve, which was y squared. I forgot to change it into x's. And I need, the orange is my radius. All right, so, shell radius. Step 2, find the limits of integration. I think we should be a little bit pros now about how to do this. If we're not given it, we're going to set a few things equal to each other. So 3, we are going to integrate 2 pi times shell height times shell radius. All right. So with respect to we call it this is the silliest term. It's called the thickness variable. So that thickness variable, remember we had delta x all the way up here. I know if you're writing notes, I'm just like moving all along. So right here, delta x was our thickness variable. Right here, our thickness variable was y, because if I made my cylindrical shells thicker, they would go like thicker this way, and so on. So those were y's. Thickness variable, which is either going to be x or y. Hopefully the only 2 variables you have. And we do all that to find the volume. I know those were only 2 short examples, but, or actually it was 3. Your homework is going to be a lot more helpful, more practice with this, just to see more problems. It's really going to help, I promise you. So let me know if you have any questions, comments, concerns. It's been a great semester, and I will see you guys in the review tomorrow. Bye!